In the deepest stretches of space where galaxies are expected to gather and light should slowly accumulate, astronomers have found something unexpectedly quiet. Vast regions where almost nothing seems to reside. Ancient light arriving alone. Structures appearing isolated, suspended in darkness, separated by distances so large they resist intuition. Welcome to the Sleepy Scientist. If drifting through questions like this helps the mind slow and settle, you're very welcome here. Sharing where in the world you're listening from tonight is always appreciated. It is comforting to know how far into the void thoughts travel. Over the past few decades, increasingly sensitive instruments have traced faint signals from the edge of what can be seen. Telescopes placed above Earth's atmosphere, and others sent far beyond it, have slowly revealed a universe that feels less crowded than once imagined, less centered, more uneven, large expanses where galaxies thin out, giving way to enormous regions of near emptiness. As these observations accumulated, another pattern became impossible to ignore. Space itself is expanding, not dramatically or violently, but steadily and without pause. The farther away a galaxy lies, the faster it appears to drift from view. Beyond a certain distance, light never arrives at all, not because nothing exists there, but because the universe has stretched too far, too fast, for that light to reach this small corner of space. What might first appear as an edge begins to look more like a limit, a horizon shaped not by walls or endings, but by time, expansion, and the finite speed at which information can travel. A gentle boundary where observation fades, even though reality may continue uninterrupted beyond it. Modern observatories continue to push this boundary outward, peering deeper into cosmic history and refining measurements of where matter gathers and where it does not. Each new survey sharpens the picture, while quietly reminding just how much remains unseen. Tonight's journey explores one of those quiet absences, not the edge of the universe, but a vast region within it, a place sometimes described as a cosmic void, a subtle hollow in the large-scale structure of space, and possibly part of the environment the Milky Way itself inhabits. Settle in and let the universe stretch outward, slowly. For much of human history, the universe was assumed to be calm, orderly, and evenly filled. When early astronomers looked into the night sky, what they saw appeared smooth and continuous. Stars were scattered across the darkness. Faint smudges of light hinted at distant galaxies, and there was little reason to suspect that matter arranged itself in any particularly dramatic way. With limited instruments and a narrow field of view, the cosmos seemed broadly uniform, like a fine mist spread gently through space. This expectation made sense. When observations are shallow, large patterns are hard to detect. From a great distance, even a crowded city can appear evenly lit, its streets and neighborhoods blending into a soft glow. Early telescopes offered a similar impression of the universe. Individual galaxies could be identified, but the spaces between them were poorly resolved. The prevailing idea was simple and comforting. On the larger scales, matter should be spread out more or less evenly, with no preferred locations and no vast gaps. As telescopes improved, that calm picture began to soften. Astronomers noticed that galaxies were not randomly sprinkled across space. They tended to gather. Groups of galaxies appeared bound together, moving in slow gravitational dances. These collections were not rare exceptions. They were common. Over time, clusters containing hundreds or even thousands of galaxies were identified, each one held together by gravity and embedded in regions of space that seemed far busier than their surroundings. Between these clusters, something unexpected emerged. There were regions with very few galaxies at all, not just fewer than average, but dramatically fewer. Wide expanses where telescopes found almost nothing. At first, these gaps were treated with caution. It was tempting to assume the observations were incomplete, that faint galaxies were simply being missed. But as surveys expanded and instruments became more sensitive, the pattern persisted. Dense regions and sparse regions repeated themselves over and over again. Understanding this structure required more than just counting galaxies. It required knowing how far away they were. This is where light itself became a measuring tool. As galaxies move away through expanding space, the light they emit stretches as it travels. Its colour shifts toward longer wavelengths, a gentle reddening that carries information about distance. The farther a galaxy lies, the more its light has been stretched during its journey. By carefully measuring this stretching, astronomers could estimate how far away a galaxy was, not just where it appeared on the sky. Direction alone gives a flat picture. Distance adds depth. When millions of these measurements were combined, the universe began to reveal its true shape. What once looked like a smooth fog transformed into something textured and intricate. Large surveys mapped not hundreds, not thousands, but millions of galaxies. Each one was placed into a three-dimensional map, its position determined by where it appeared and how much its light had stretched along the way. When these maps were viewed as a whole, a striking pattern emerged. Galaxies were not scattered randomly. They traced long, delicate strands that stretched across enormous distances. These filaments connected dense nodes where clusters gathered, forming a vast interconnected network. Between these filaments lay enormous empty regions. These were not small gaps, but vast volumes of space, sometimes tens or even hundreds of millions of light-years across, containing very few galaxies. These regions came to be known as voids. The name can sound dramatic, but the reality is quieter. A void is not a hole punched into the universe. It is a region where matter is sparse, not absent. Together, clusters, filaments, and voids form what is often called the cosmic web. The name is fitting. Like a spider's web glistening in early morning light, the structure is delicate, expansive, and held together by invisible forces. Gravity acts as the thread, drawing matter toward dense regions while allowing emptier areas to grow even emptier over time. It is important to understand what emptiness means in this context. A cosmic void is not a place where physics stops working. Gravity still operates there. Time still flows. Space still expands. Even in the emptiest regions, there is dark matter, faint gas, and the quiet background glow left over from the early universe. The difference is one of degree, not existence. These regions simply never accumulated much matter to begin with. In the early universe, matter was distributed almost evenly, but not perfectly so. Tiny variations in density were present from the very beginning. Over billions of years, gravity amplified those small differences. Regions that were slightly denser pulled in more matter, growing into filaments and clusters. Regions that were slightly less dense lost material to their surroundings, gradually becoming voids. The universe did not carve out empty spaces deliberately. It followed the slow, patient rules of gravity, and structure emerged naturally. This understanding changed how astronomers think about emptiness. Voids are not failures of formation, or gaps waiting to be filled. They are essential components of the universe's architecture. Their presence shapes how galaxies move, how structures grow, and how matter flows on the largest scales imaginable. In a very real sense, the universe is defined as much by where matter is scarce, as by where it is abundant. There is a gentle irony in this. The most dramatic discoveries about cosmic structure came not from where galaxies are, but from where they are not. By mapping absence, astronomers uncovered order. By tracing empty regions, they revealed a hidden framework underlying everything that can be seen. Seen this way, the universe is not smooth, but it is not chaotic either. It is patterned, shaped by simple laws acting over vast spans of time. Filaments stretch, clusters gather, and voids open quietly between them. Nothing about this process is rushed. Nothing is abrupt. It is a slow unfolding written in light that has travelled for billions of years to arrive here at all. When the night sky looks calm and evenly scattered, it is not misleading so much as incomplete. Beneath that gentle appearance lies a universe woven together by gravity, where structure emerges from subtle beginnings and emptiness plays as important a role as matter itself. When astronomers speak about a void, the word can sound more dramatic than the reality it describes. In everyday language, a void suggests absolute emptiness, a complete absence, a hole where nothing exists at all. In the universe, a cosmic void is something quieter and far more subtle. It is not a place where matter disappears. It is a place where matter never gathered very much in the first place. A useful way to think about a cosmic void is as a region of unusually low density. Compared to the surrounding universe, very little is collected there. Galaxies are sparse, gas is thin, the familiar glow of stars becomes rare. But none of this means the region is empty in any absolute sense. Physics still applies, gravity still shapes motion, space still expands. Time still moves forward at its unhurried pace. Cosmic voids come in a wide range of sizes, and this is where scale begins to challenge intuition. Some are relatively modest by cosmic standards, spanning distances comparable to clusters of galaxies. Others are truly enormous, stretching across tens or even hundreds of millions of light years. To place that gently into perspective, light from one side of such a region could begin its journey long before complex life appeared on Earth, and only arrive at the other side long after humanity had begun to look up at the stars. Despite their size, voids are not sharply defined objects. There are no hard edges or visible walls. Instead, density changes gradually. Galaxies become less frequent, then rarer still. Eventually, the familiar patterns of clusters and filaments fade into long stretches of space where only the faintest traces remain. It is a slow thinning rather than a sudden drop. Even within these sparse regions, matter persists. Dark matter, which outweighs ordinary matter throughout the universe, continues to thread through voids, though in lower concentrations. Thin gas drifts quietly, spread across enormous volumes. Occasionally faint galaxies can be found, often small, isolated and evolving slowly. These galaxies tend to live quieter lives, forming stars at a more relaxed pace, shaped by isolation rather than constant interaction. Because voids are not empty, they are not static. Matter still moves within them, responding to the gravitational pull of denser regions nearby. In fact, voids slowly expand as surrounding filaments and clusters draw material away. Over time, this makes voids emptier, not because anything is being removed deliberately, but because gravity elsewhere is doing its steady work. Defining where a void begins and ends is less straightforward than naming it. Astronomers do not draw boundaries by sight alone. Instead, they rely on careful measurements of galaxy distribution. Regions where galaxy density drops below a certain level are identified as voids. The precise threshold depends on the method being used, but the idea remains the same. A void is defined by contrast. It exists because surrounding regions are richer. Mathematically, these boundaries can be described using algorithms that search for large connected volumes of low density. The mathematics behind this process can be complex, but the result is intuitive. When plotted on a map of the universe, voids appear as vast open spaces surrounded by luminous threads. Seen visually, the structure feels almost organic, like bubbles packed together, each one shaped by the pressure of its neighbours. From a human perspective, voids can feel unsettling. There is something instinctively uncomfortable about large empty spaces, especially when they are measured on scales that defy everyday experience. But in cosmology, voids are not signs of absence or failure. They are natural outcomes of how matter evolved from a nearly uniform beginning into a structured universe. In the early universe, matter was spread out with remarkable uniformity. Tiny fluctuations existed, but they were incredibly small. Over time, gravity amplified those slight differences. Dense regions grew denser. Sparse regions lost material to their surroundings. This slow process, unfolding over billions of years, naturally produced a landscape of peaks and valleys. Clusters became the peaks. Voids became the valleys. What makes voids particularly interesting is that they are among the most stable environments in the universe. With fewer interactions and weaker gravitational disturbances, structures inside voids evolve gently. Changes happen slowly. In a sense, voids preserve a quieter record of cosmic history, offering a glimpse of how matter behaves when left largely undisturbed. There is also a subtle beauty in how voids fit into the larger picture. The universe does not organize itself by filling every available space evenly. Instead, it creates contrast. Dense regions and empty regions grow together, shaping one another. Without voids, filaments would have no definition. Without emptiness, structure would blur. This is why astronomers do not treat voids as empty mistakes scattered between important objects. They are essential features of the cosmic landscape. Their size, shape, and distribution carry information about the universe's composition, its expansion, and the invisible matter that shapes everything seen and unseen. It is worth noting that voids are not identical to one another. Some are rounder, others are stretched by surrounding structures. Some contain a handful of faint galaxies, others are nearly pristine. These differences tell stories about their local environments and the slow gravitational conversations taking place across cosmic time. Perhaps the most calming aspect of cosmic voids is their patience. Nothing about them is sudden, nothing collapses or vanishes. They grow quietly as matter elsewhere gathers. They expand gently as space itself stretches. Their emptiness deepens not through destruction, but through redistribution. So when astronomers speak of a void, they are not describing nothingness. They are describing balance. A region defined not by what is missing, but by how matter has chosen, through gravity and time, to arrange itself elsewhere. In this way, voids are as much a part of the universe's structure as galaxies themselves. Seen from afar, the universe resembles a vast, delicate pattern, woven from matter and absence together. Voids are the spaces that allow that pattern to breathe. They give shape to the cosmos not by being empty, but by being gently, patiently less full. When astronomers talk about the Milky Way's neighbourhood, they are not imagining a tidy cluster of nearby galaxies packed closely together. The word neighbourhood can be misleading, because in everyday life it suggests proximity, familiarity, and density. In the universe, those ideas quickly drift apart. What matters most is scale, and scale has a habit of reshaping meaning. The most immediate environment of the Milky Way is known as the local group. This is a small collection of galaxies bound together by gravity, moving through space as a loose family. It contains a few large members, including the Milky Way itself and a nearby spiral galaxy often called our closest large companion, along with dozens of much smaller galaxies. These smaller systems are faint, irregular, and often overlooked, yet they make up the majority of the group. Even within this local gathering, space dominates. The distances between galaxies are enormous compared to their sizes. If the Milky Way were reduced to the size of a coin, its nearest large neighbour would still be many meters away. The local group feels intimate only by cosmic standards. In human terms, it is astonishingly empty. This is the first lesson of cosmic neighborhoods. Being close does not mean being crowded. Galaxies can share a gravitational relationship while remaining separated by vast distances of darkness. The universe allows companionship without closeness, structure without density. Beyond the local group, the definition of neighborhood begins to stretch. Astronomers often expand the scale to include nearby groups and clusters of galaxies, forming larger associations sometimes described as local volumes or superclusters. At each step outward, the word nearby loses its everyday meaning and becomes purely relative. What counts as close depends entirely on the frame of reference. From one perspective, the Milky Way sits in a modest group of galaxies, quietly orbiting a shared centre of mass. From another, that entire group is just one small knot within a much larger arrangement of matter. Neither view is wrong. Each simply describes a different level of zoom. As astronomers mapped the motion of galaxies in and around our region of space, they noticed something subtle but important. Galaxies were not moving randomly. Their motions carried information about what surrounded them, including things that could not be seen directly. Some galaxies appeared to drift in ways that suggested they were being pulled toward distant concentrations of mass. Others seemed to move away from the large empty regions, as though pushed by an absence rather than pulled by a presence. These motions are gentle, measured over long periods, but they are consistent. They reveal that gravity responds not only to what is nearby, but to the broader distribution of matter across space. Dense regions exert influence. Sparse regions do as well, not by pulling, but by offering less resistance, allowing surrounding structures to dominate the motion. This means that understanding the Milky Way's neighborhood requires more than counting nearby galaxies. It requires understanding the balance between dense regions and emptier ones. A galaxy can have neighbors and still sit on the edge of a much larger empty region. Proximity on one scale can coexist with isolation on another. When astronomers describe where the Milky Way is located, they often do so in layers. First, there is the galaxy itself, a spiral system of stars, gas, and dust. Then comes the local group, a small gravitational community. Beyond that lies a broader region containing other groups and filaments, and beyond that still, immense stretches where galaxies become scarce. Each layer adds context, each one shifts perspective. At no point does the universe offer a single definitive address. This layered view helps explain why discussions of cosmic location can sound contradictory. One description might emphasize companionship, noting that the Milky Way is part of an active group of galaxies. Another might emphasize emptiness, pointing out that this group sits near a region where matter is unusually sparse. Both statements can be true at the same time. Distance alone does not define environment. Density matters just as much. A galaxy can be surrounded by neighbors yet still exist in a broader region, where galaxies are few and far between. In that sense, cosmic neighborhoods are not fixed zones with clear boundaries. They are gradients, fading from busy to quiet over immense scales. The motions of galaxies help reveal these gradients. By observing how nearby galaxies move relative to one another, astronomers can infer where mass is concentrated and where it is lacking. These motions act like subtle signposts, pointing toward dense filaments and away from large empty volumes. Even without seeing the full structure directly, the universe leaves clues in how it moves. What emerges from this picture is a sense that location in the universe is deeply contextual. The Milky Way is not isolated in the way a single star might be isolated in deep space, nor is it packed into a dense cluster where interactions are constant and dramatic. It occupies a middle ground, shaped by both companionship and distance, This balance has consequences. Galaxies in dense clusters experience frequent interactions, collisions, and disruptions. Galaxies in emptier regions evolve more quietly, shaped by internal processes rather than constant external influence. The Milky Way's position suggests a relatively calm history, with enough interaction to shape its structure, but enough space to avoid continual disturbance. There is a gentle irony here. From within the Milky Way, the night sky feels rich and crowded, filled with stars. From the perspective of the local group, the Milky Way is one luminous island among a few others. From a still broader view, that entire island chain drifts near a region of comparative emptiness. The sense of abundance and the sense of isolation coexist, depending on where the boundary is drawn. Astronomers are careful with this language for a reason. Words like neighborhood, nearby, and local are conveniences, not absolutes. They help organize understanding, but they do not describe rigid structures. The universe resists sharp divisions. Everything blends gradually into something larger. Seen this way, mapping the Milky Way's neighborhood is less about pinning down a precise location and more about understanding relationships. Who is close on one scale? Who is distant on another? Where matter gathers, where it thins? How gravity connects regions across distances that defy intuition. This perspective encourages a quieter way of thinking about place. Instead of asking whether the Milky Way is isolated or connected, it becomes more useful to ask in what way and at what scale. The answer changes as the view widens, and that change is not a flaw. It is a feature of a universe built on layers of structure. In the end, the Milky Way's neighborhood is not a single thing. It is a nested arrangement of environments, each one revealing something different about how matter organizes itself. Close companions exist alongside vast spaces. Motion reveals both attraction and absence. Location becomes a matter of perspective, shaped by how far one chooses to look. And perhaps that is the most important lesson of all, in the universe, where something cannot be separated from how it is viewed. The Milky Way is neither crowded nor alone. It is situated contextually within a structure that depends entirely on scale. Close to home, on cosmic scales, there is a region of space that at first seems almost unremarkable. No dramatic name drawn from mythology, no sudden edge or visible boundary, just an unusually quiet stretch of the universe, identified not by what it contains, but by what it lacks. Astronomers call it the local void, and despite the simplicity of the name, it represents one of the most intriguing features of our immediate cosmic environment. The local void is not a theoretical idea or a poetic description. It is a real, studied structure, recognized through decades of careful observation. Its existence became clear not through a single discovery, but through a growing pattern that refused to disappear as data improved. When astronomers mapped nearby galaxies, they noticed a broad region of space where galaxies were unexpectedly scarce. Telescopes looked there and kept finding very little. At first, this absence was treated cautiously. Observational gaps are common in astronomy, especially when faint objects are involved. It is always possible that something is simply too dim to be detected. But as surveys expanded and instruments became more sensitive, the emptiness remained. The region was not missing galaxies because of poor data. It was missing galaxies because there were very few to find. The local void revealed itself in another way as well, through motion. Galaxies near this region did not sit still. They moved in patterns that hinted at an imbalance in their surroundings. Instead of drifting evenly in all directions, many nearby galaxies appeared to be moving away from the void. Not dramatically, and not suddenly, but persistently. Over time, these motions painted a consistent picture. Gravity provides the explanation, and it does so quietly. Dense regions of space pull matter toward them, Sparse regions pull less. When a large volume contains very little mass, it exerts relatively weak gravitational influence. Surrounding structures richer in matter dominate instead. The result is not that galaxies are pushed by some force emanating from the void, but that they are drawn more strongly toward denser regions elsewhere. This distinction matters. The local void is not expelling galaxies. It is simply failing to hold on to them. Over billions of years, matter has drifted toward filaments and clusters, leaving behind a growing region of low density. The motions we observe today are the gentle outcome of that long process. The Milky Way sits close to this region, but not within its deepest interior. Observations indicate that our galaxy lies near the edge of the local void, close enough to feel its influence, but far enough to remain part of a more populated environment. This positioning helps explain certain features of local galaxy motion without placing the Milky Way in an extreme or unusual location. Being near the edge of a void is different from being surrounded by emptiness. The night sky still contains nearby galaxies. The local group remains intact. Gravity from neighbouring structures continues to shape motion and evolution. Yet the presence of a large underdense region nearby subtly affects the broader flow of matter. This edge position is revealed through careful measurements of galaxy velocities. When astronomers compare the motion of nearby galaxies to what would be expected in a perfectly uniform universe, small deviations appear. These deviations are not random. They align with the direction of the local void. Galaxies on one side show motions consistent with being drawn toward denser regions on the opposite side. Again, nothing here is abrupt. The speeds involved are modest by cosmic standards. These are slow drifts measured over vast spans of time, but they are consistent, and consistency is the currency of careful science. The local void itself is large, extending across tens of millions of light-years. Within this volume, galaxies are rare but not entirely absent. A handful of faint systems exist, often small and isolated. Their presence confirms that the region is not empty, just sparse. These galaxies tend to evolve quietly, shaped more by internal processes than by frequent encounters. The shape of the local void is not perfectly round or symmetrical. Like most cosmic structures, it is shaped by its surroundings. Filaments and galaxy groups define its boundaries, pressing in from different sides. The void expands where resistance is weakest and slows where denser structures limit its growth. This gives it an irregular organic form rather than a simple geometric one. What makes the local void particularly interesting is its proximity. It's not a distant curiosity visible only through deep surveys of the far universe. It is part of the environment through which the Milky Way itself moves. Its influence is subtle, but it is present, quietly shaping local dynamics. Despite this, the local void is not treated as an anomaly. It fits comfortably within the broader understanding of how the universe evolves. Similar voids are found elsewhere, scattered throughout the cosmic web. The local void is special only because it is nearby, not because it breaks any rules. This nearness does invite closer scrutiny. The more detailed the observations become, the clearer it is that voids play an active role in shaping motion, even if they do so passively. By being regions of low density, they help define where matter flows, how structures grow, and how galaxies drift over time. There is something gently counterintuitive about this. We're used to thinking of influence as something exerted by presence. In the universe, absence can matter too. A lack of mass changes the gravitational landscape just as surely as an excess does. The local void contributes to the balance of forces shaping our region of space simply by being less full than average. From a human perspective, the idea of living near a vast empty region can sound unsettling. In reality, it is neither dangerous nor unusual. The universe is filled with such contrasts. dense regions and empty ones exist together, each giving shape to the other. The Milky Way's position near the edge of a void is a natural outcome of that pattern. There is also a certain calmness to this picture. Nothing is rushing, nothing is being torn apart. The motions involved are slow and steady, unfolding over timescales far beyond any human concern. The local void is not expanding aggressively or swallowing nearby galaxies. It is simply becoming emptier as matter elsewhere continues to gather. Astronomers approach this region with care and restraint. Observations are compared, models refined, and conclusions drawn conservatively. The goal is not to dramatize emptiness, but to understand structure. The local void is a reminder that the universe's architecture includes silence as well as brilliance. Seen in this light, the local void is not a gap in the universe, but a quiet participant in its ongoing evolution. It is a nearby example of how matter and space arrange themselves over time, guided by gravity and shaped by initial conditions set billions of years ago. The Milky Way's relationship with this region is one of proximity, not immersion, close enough to notice, far enough to remain part of a richer environment. It is a position defined by balance and by perspective. In the end, the local void tells a simple story told on an enormous scale. Matter doesn't fill space evenly. It gathers, it thins, and it flows. Where matter gathers, structure shines. Where it thins, quiet expands. Both are necessary, both are real, and both are present, quietly shaping the space we call home. At first glance, it might seem as though galaxies are actively avoiding certain regions of the universe, as if vast areas of space have been marked off limits. In reality, nothing is being avoided at all. What looks like preference is simply the long, patient outcome of gravity doing what it has always done, quietly and without intention. In the earliest moments after the universe began, matter was spread out with remarkable uniformity. Not perfectly smooth, but close enough that the differences were almost unimaginably small. Some regions contained just a little more matter than average, others contained just a little less. These differences were tiny, far too small to notice without sensitive instruments, but they mattered. Gravity responds to mass wherever it appears. Even the slightest excess begins to pull on its surroundings. Over time, regions that started out slightly denser drew in more matter from nearby space. That extra matter increased their gravitational pull, which drew in even more material. This process is known as gravitational amplification, though there is nothing sudden or explosive about it. It is slow, steady, and deeply patient. A helpful way to picture this is to imagine a landscape after gentle rain. Water does not rush everywhere equally. It drifts toward the lowest points. Shallow dips gather more water, becoming deeper pools, while slightly raised areas drain and dry out. No part of the landscape is choosing where the water goes. The flow is guided entirely by small differences in height. Over time, those differences become more pronounced. The universe followed a similar path. Regions that began with a slight excess of matter became the seeds of future structure. As gravity drew material inward, these regions grew into filaments and clusters of galaxies. At the same time, regions that started with slightly less matter lost what little they had to their denser neighbours. These areas gradually became emptier, not because matter was removed, but because it was never replaced. This is why dense regions grow denser and empty regions grow emptier. Gravity does not spread matter evenly, it concentrates it, and once a region begins to lag behind in density, it becomes increasingly unlikely to catch up. The universe does not correct these imbalances, it amplifies them gently, over billions of years. Voids emerge naturally from this process. They are not carved out. They are not blown open. They simply fail to accumulate matter as efficiently as their surroundings. As filaments thicken and clusters grow heavier, voids expand, stretching quietly as space itself continues to grow. It is important to emphasize that nothing dramatic happens inside a void to drive this process. There is no force pushing matter away. There is no pressure evacuating space. Matter flows outward because gravity elsewhere is stronger. Dense regions act like deep basins, slowly drawing material inward. Sparse regions act like gentle slopes, offering little resistance as matter drifts away. Over immense spans of time, this creates the large-scale structure observed today. Filaments thread through space, connecting massive clusters, while voids open between them like broad, calm valleys. The pattern is not random. It is the inevitable outcome of simple rules applied consistently over an unimaginably long duration. The pace of this evolution is almost difficult to describe without understating it. Changes unfold over hundreds of millions, even billions of years. Nothing happens suddenly. Galaxies drift, matter flows, structures grow incrementally. From a human perspective, everything appears frozen. From a cosmic perspective, everything is in motion. One reason this process feels counterintuitive is that everyday experience rarely deals with gravity acting over such vast distances. On Earth, gravity pulls objects straight downward, and its effects feel immediate. In space, gravity acts sideways, gently nudging matter over enormous distances. The result is not falling, but drifting. Not collapse, but slow gathering. This drifting helps explain why galaxies can move away from voids without being pushed. Imagine standing on a wide, flat plain with shallow hills in the distance. Walking toward a hill does not require being pushed from behind. It happens naturally because the terrain slopes downward toward the hill. In the universe, dense regions create a similar slope in the gravitational landscape. As matter continues to flow toward denser regions, voids do not remain static. They grow larger and emptier over time. Their boundaries shift slowly as filaments thicken, and clusters draw in material from ever farther away. This expansion is gentle and orderly, shaped by the surrounding distribution of mass. Despite their emptiness, voids still play an active role in cosmic evolution. By defining where matter is scarce, they help determine where matter gathers. Filaments stretch between clusters, partly because voids surround them, shaping their paths like channels guiding slow-moving currents. There is also an important balance at work. The universe does not collapse entirely into a single dense region, nor does it spread out evenly forever. Expansion and gravity compete, shaping structure without erasing it. Voids and clusters coexist, each reinforcing the presence of the other. This balance produces a universe that is neither smooth nor chaotic. It is structured, but softly so. Patterns emerge, but without sharp edges. Growth happens, but without urgency. In this environment, voids are not signs of failure or incompleteness. They're expected outcomes of cosmic growth. Occasionally, it is tempting to imagine that voids represent places where something went wrong, where galaxies failed to form. In truth, they represent places where galaxies were never strongly encouraged to form. The initial conditions simply did not favor accumulation. Over time, that small disadvantage became a defining feature. There is a quiet elegance in this process. From tiny variations in density, the universe built a vast architecture of light and darkness. No guiding hand was required. No corrections were made. Gravity followed simple rules, and structure emerged naturally. Gentle humor sometimes helps here. If the universe were a party, galaxies would gather where the music is loudest, not because anyone told them to, but because that is where energy and activity collect. The quiet corners remain quiet, not out of neglect, but because nothing draws the crowd there. Seen this way, voids are not empty spaces waiting to be filled. They are calm regions that grew naturally as matter elsewhere gathered together. Their existence is a testament to how small beginnings can shape enormous outcomes. Understanding why galaxies avoid certain regions is really about understanding why gravity favours some places over others. It is a story of amplification, not exclusion, of growth, not rejection, of a universe that evolves patiently, guided by simple principles applied consistently across vast scales. In the end, galaxies do not avoid voids, they drift toward opportunity. Dense regions offer stronger gravitational pull, richer environments, and more interaction. Sparse regions offer none of these things. Over time, that difference matters. What remains is a universe shaped by slow-moving tides of matter, flowing across space, gathering where gravity invites it, and thinning where it does not. Voids are the quiet spaces left behind by this long journey, natural and inevitable, woven into the very fabric of cosmic history. Much of what shapes the universe cannot be seen directly. Stars and galaxies provide light, but they do not tell the whole story. Beneath that visible layer lies an unseen framework that quietly determines where matter gathers and where it thins. This hidden influence is known as dark matter, and its role in shaping cosmic structure is subtle, persistent, and remarkably effective. Dark matter does not glow, reflect, or absorb light in any familiar way. Telescopes cannot photograph it, yet its presence is revealed through motion. Galaxies rotate faster than visible matter alone can explain. Clusters hold together more tightly than their luminous contents allow. On the largest scales, patterns of structure align with something invisible but massive. Dark matter announces itself not by shining, but by pulling. From the earliest stages of the universe, dark matter played a leading role. While ordinary matter interacted with light and heat, dark matter moved differently. It did not slow down in the same way. It began to clump early, forming faint gravitational wells long before stars or galaxies appeared. These wells became the scaffolding upon which visible structure later assembled. As ordinary matter cooled and began to gather, it fell into these invisible concentrations. Gas flowed inward. Stars ignited. Galaxies formed where dark matter had already gathered. In this sense, dark matter did not follow galaxies. Galaxies followed dark matter. This process helps explain why galaxies appear where they do. Dense regions of dark matter became homes for clusters and filaments. Sparse regions where dark matter was less concentrated became the quiet expanses now known as voids. The distribution of visible matter mirrors the distribution of dark matter, but only imperfectly. Light traces structure. Gravity defines it. It is important to note that voids are not empty of dark matter. They contain it too, just in lower concentrations. Even the quietest regions of space are threaded with this invisible material. The difference is not presence versus absence, but abundance versus scarcity. Where dark matter is dense, galaxies flourish. Where it is thin, galaxies are few. This understanding did not emerge overnight. Long before detailed maps of galaxies existed, physicists began simulating how the universe might evolve under the influence of gravity and dark matter. These simulations started with simple initial conditions, small variations in density, and well-tested physical laws. Then they were allowed to run forward in time. The results were striking. Without being instructed to produce filaments or voids, the simulations generated them naturally. Dense nodes formed, long strands connected them, vast empty regions opened in between. The overall pattern closely resembled what later surveys would observe in the real universe. In many cases, these simulated voids appeared before astronomers had the observational data to confirm them. As galaxy surveys improved, the predicted structures began to appear in real maps. This alignment between theory and observation became one of the quiet successes of modern cosmology. That success is worth appreciating without exaggeration. The simulations do not capture every detail. They simplify complex processes. They rely on assumptions that continue to be tested and refined. But the fact that such large-scale features emerged at all speaks to the strength of the underlying ideas. Dark matter acts as an organizer rather than a designer. It does not plan structure, it responds to gravity. Over time, its influence creates a framework within which visible matter arranges itself. Voids, in this picture, are not anomalies. They're expected outcomes wherever dark matter density remained low. Because dark matter dominates the mass of the universe, its distribution has a powerful influence on motion. Galaxies drift along paths shaped by this invisible landscape. Filaments act like gentle channels, guiding matter toward dense regions. Voids become areas of relative gravitational quiet, where matter moves outward simply because stronger pulls lie elsewhere. This perspective helps clarify why voids grow over time, as dark matter continues to clump in filaments and clusters. Surrounding regions lose relative influence. Matter flows away slowly, deepening the contrast. The universe becomes more structured, not because something is being actively rearranged, but because gravity continues to act on what was already uneven. One of the most reassuring aspects of this picture is its consistency. The same principles that explain galaxy rotation explain cluster stability. The same framework that predicts filaments also predicts voids. Dark matter provides a unifying explanation across scales that differ by millions of times. At the same time, there is humility built into this understanding. Dark matter is inferred, not observed directly. Its nature remains unknown. Whether it is made of undiscovered particles or something even more subtle is still an open question. The success lies not in knowing what dark matter is, but in knowing what it does. That distinction matters. Scientific confidence does not require complete understanding. It requires consistent explanation. Dark matter earns its place in cosmology not through certainty of composition, but through its ability to account for observed patterns again and again. In the context of voids, this means predictions can be made carefully. Simulations suggest how voids should evolve, how empty they should become, and how they should influence nearby motion. Observations broadly support these expectations. Where discrepancies appear, they guide refinement rather than rejection. There is also a gentle lesson here about invisibility. The most influential component of cosmic structure cannot be seen. Light, for all its usefulness, traces only a small fraction of what exists. The quiet architecture of the universe is built largely from something that leaves no direct visual imprint. This does not diminish the role of visible matter. Stars, galaxies, and gas provide the details that make the universe rich and varied. But the underlying shape comes from something quieter. Dark matter sets the stage. Ordinary matter performs upon it. Even humour finds a place here. If the universe were a city, dark matter would be the street layout, zoning rules, and infrastructure, quietly determining where buildings can rise. Galaxies would be the lights in the windows, visible and lively, but following patterns laid down long before anyone moved in. Seen this way, voids are not empty neighbourhoods waiting to be developed. They are regions where the infrastructure was never dense enough to encourage growth. Nothing failed to arrive. There was simply little reason to stay. The predictive success of dark matter-based models does not mean the story is complete. Questions remain. Details continue to be explored. Alternative ideas are tested. This is not uncertainty in the sense of confusion, but uncertainty in the sense of ongoing refinement. What stands firm is the broad picture. An invisible component shapes where matter gathers, that shaping produces filaments, clusters, and voids. The patterns seen in simulations align closely with what is observed. The quiet role of dark matter leaves a visible imprint across the universe. In the end, dark matter reminds observers that the universe is guided as much by what cannot be seen as by what can. Its influence is steady, unhurried, and vast. It does not announce itself. It does not demand attention. Yet without it, the universe would look profoundly different. Voids, filaments, and galaxies together tell a story written largely in invisible ink. Dark matter provides the grammar. Gravity supplies the rhythm. Visible matter fills in the detail. And over billions of years, a structured universe emerges, calm, intricate, and quietly held together by forces that work best when they remain unseen. To understand why the universe looks the way it does, astronomers do something that might seem counterintuitive at first. They build a universe from scratch. Not with stars or galaxies, but with numbers, rules, and patience. These constructions are known as cosmological simulations, and they offer a quiet window into how structure emerges over time. A simulation usually begins with a simple starting point. Matter is spread out almost evenly, with only tiny variations in density. These variations are not invented for convenience. They're based on measurements of the early universe, when everything was still hot, smooth, and remarkably uniform. From this near balance, the simulation is allowed to evolve. Gravity is the main driver. Each small region of matter pulls on every other, according to well-tested physical laws. Expansion is included as well, allowing space itself to stretch as time passes. Ordinary matter and dark matter are treated differently, reflecting how they behave in the real universe. Nothing else is added. No special instructions are given for forming galaxies, filaments, or voids. Then time is allowed to run forward, not seconds or years, but billions of years, compressed into a sequence of small steps. With each step, matter shifts slightly. Dense regions pull in more material. Sparse regions lose what little they have. Patterns that were invisible at the beginning begin to take shape. At first, the changes are subtle. The universe still looks mostly smooth. But as time accumulates, structure becomes clearer. Small clumps grow larger. Threads begin to stretch between them. Regions between these threads become emptier. Without being told to do so, the simulation begins to resemble the observed universe. Voids appear early and persist. They do not require special conditions. They emerge naturally whenever gravity is allowed to amplify small differences over long periods. Nearly every simulation that starts with realistic conditions produces them. The shapes vary, the sizes differ, but the presence of large, underdense regions is consistent. What makes this particularly reassuring is how these simulated patterns compare to real observations. When astronomers map galaxies across the sky and place them into three-dimensional space, the resulting structures look strikingly familiar. Long filaments connect dense clusters, wide voids open between them. The overall geometry aligns closely with what simulations predict. The resemblance is not perfect, and it does not need to be. The universe is complex, and simulations simplify many details. Star formation, gas behavior, and galaxy interactions are treated in approximate ways. Yet the large-scale structure emerges correctly, even when those details are handled gently. This suggests that the biggest features of the universe are shaped by simple, robust processes. Gravity, expansion, and initial conditions do most of the work. The fine details add texture, but the broad pattern is already set. One of the strengths of simulations is that they allow astronomers to experiment without disturbing anything real. Conditions can be adjusted slightly. The amount of dark matter can be changed. The rate of expansion can be varied. Each change produces a slightly different universe. By comparing these outcomes to observations, scientists learn which assumptions matter most. In nearly all reasonable versions of these simulated universes, voids appear. They are not optional features, they are consequences. Remove them, and the rest of the structure no longer matches what is seen in the sky. These digital universes also show how voids evolve. Early on, they are shallow and poorly defined. Over time, they expand and deepen as matter flows outward. Their boundaries sharpen as filaments grow thicker. The contrast between dense and sparse regions increases slowly, giving the universe its present texture. Despite the immense scales involved, the process is gentle. Nothing snaps into place. Nothing collapses suddenly. Everything unfolds gradually, guided by gravity acting over long distances. The universe takes its time, and the simulations reflect that patience. There is also a comforting predictability to the outcome. Start with a universe that is almost smooth. Let gravity operate. Allow time to pass. Structure appears, filaments stretch, voids open. This happens not once, but again and again across different models and different assumptions. Of course, simulations are not perfect replicas of reality. They are tools. They highlight what is essential and simplify what is secondary. Their value lies not in exact duplication, but in pattern recognition. When the same features appear repeatedly under varied conditions, confidence grows that those features reflect something fundamental. This is why astronomers place trust in the large-scale picture even while debating the details. Voids, clusters, and filaments are not fragile predictions. They are sturdy outcomes of gravity acting in an expanding universe. There is a gentle humour in watching a universe assemble itself inside a computer. No instructions are given for beauty or balance, yet something orderly emerges. Without guidance, a complex structure forms. Shaped by rules so simple they can be written in a few lines of code, yet powerful enough to shape everything. If the universe were a long story, simulations allow astronomers to reread it from the beginning, adjusting the lighting slightly each time to see which features stand out. No matter how the scene is illuminated, the same broad shapes appear. This consistency does not mean that every mystery is solved. Simulations continue to improve as computing power increases and understanding deepens. Small discrepancies remain. New questions emerge. This is part of the process, not a flaw. What simulations provide, above all, is reassurance. They show that voids are not accidents or artifacts of observation. They are expected. They arise naturally from the same processes that form galaxies and clusters. They belong to the universe's design in the same quiet way valleys belong to landscapes shaped by erosion. When observation and simulation meet, the result is not certainty, but coherence. The universe behaves as predicted, broadly and calmly. Where matter gathers, structure grows. Where it does not, space opens quietly. Seen this way, a universe with holes is not incomplete. It is working exactly as expected. Gravity pulls, expansion stretches, time allows differences to grow. And out of nearly uniform beginnings, a rich and textured cosmos takes shape, both on the screen and in the sky. The question of whether we are actually inside a cosmic hole sounds simple at first, but it quickly reveals how slippery cosmic location can be. Words like inside, outside, edge, and center work well in everyday life. They begin to lose their sharpness when applied to regions measured in tens of millions of light years. To be inside a void does not mean the same thing as standing inside a room. There are no walls to cross, no clear boundary to step over. Instead, there is a gradual change in density. Galaxies thin out. Distances between them grow larger. The environment becomes quieter, not suddenly but steadily. This makes it difficult to say exactly where a void begins or ends. Because of this, astronomers make an important distinction. There is a difference between being inside a void and being near one. Being inside suggests that the surrounding region is underdense in nearly all directions. Being near a void suggests proximity to a large empty region, while still remaining part of a more populated structure. These two situations can feel similar observationally, especially when viewed from within a galaxy. The Milky Way provides a good example of this ambiguity. From one perspective, it is part of a small group of galaxies with familiar neighbours. From another, that entire group sits next to a vast region where galaxies are rare. Whether this counts as being inside the void depends on how the boundary is defined and which scale is being considered. Cosmic scales have a way of blurring intuition. A distance that seems enormous on human terms may be modest in the context of large-scale structure. Likewise, a region that appears empty locally may sit next to something far denser, just beyond the limits of immediate observation. The universe does not organize itself into neat compartments. This is why astronomers approach questions of location carefully. Rather than asking whether the Milky Way is inside or outside a void in an absolute sense, they ask how its environment compares statistically to the average universe. Is the surrounding density higher or lower than expected? Are galaxy motions consistent with being embedded in a sparse region or merely adjacent to one? To test these ideas, astronomers rely on several lines of evidence. One comes from mapping galaxy distribution. By charting where nearby galaxies are and how densely they cluster, researchers can estimate whether our region is underdense compared to the cosmic average. These maps suggest a nearby region of low density, but also show connections to denser filaments beyond. Another line of evidence comes from motion. Galaxies do not simply sit still in expanding space. They drift slightly relative to that expansion, pulled by nearby mass concentrations. By measuring these motions, astronomers can infer the gravitational landscape around us. Patterns consistent with motion, away from a large underdense region, have been observed, supporting the idea that we are near a void. There is also the question of symmetry. If we were deep inside a large void, the surrounding universe would appear underdense in nearly all directions. Observations suggest something more uneven. Some directions show rich structures, others open into quieter expanses. This asymmetry aligns more naturally with an edge position than a central one. None of these tests provide a simple answer. They offer probabilities, tendencies, and ranges. This is not a weakness. It is how careful science works. When dealing with vast, complex systems, certainty gives way to likelihood. It is tempting to want a definitive statement. Either we live inside a cosmic hole or we do not. The reality is softer. Our location depends on how the question is framed. On smaller scales, we live in a reasonably populated neighborhood. On larger scales, that neighborhood sits near a broad region of low density. Both statements can coexist. Perspective plays a crucial role here. Imagine standing on a gently sloping hill. From one angle, the land ahead appears flat and expansive. From another, a valley opens below. Whether one says they are on a hill or beside a valley depends on where they look and how far they step back. The cosmic situation is similar, though stretched across incomprehensible distances. This layered perspective helps explain why discussions about voids can sound contradictory. Different studies emphasize different scales. Some focus on the immediate surroundings of the Milky Way. Others zoom out to tens of millions of light years. Each reveals a different aspect of the same structure. Uncertainty is not an admission of ignorance here. It is a reflection of resolution. As observational tools improve, boundaries become clearer but never perfectly sharp. There will always be regions that sit between definitions, neither fully inside nor fully outside. Astronomers are comfortable with this. The goal is not to force the universe into tidy categories, but to describe it as accurately as possible. Words are approximations, measurements are estimates. Together they form a picture that is precise enough to be useful, but flexible enough to adapt. There is also an important caution against overinterpretation. Living near a void does not place the Milky Way in a special or dangerous position. It does not alter physical laws or threaten stability. It simply means that the distribution of matter nearby is uneven, as it is almost everywhere in the universe. Many galaxies occupy similar positions. Some sit near dense clusters. Others drift along filaments. Some lie adjacent to large empty regions. None of these locations are rare or privileged. They are the natural outcomes of cosmic evolution. The idea of being inside a hole can feel unsettling because it suggests isolation. In practice, the universe does not operate on such absolutes. Connectivity exists across scales. Even near a void, gravitational influences extend far beyond immediate surroundings. The Milky Way remains part of a vast network, linked to distant structures through invisible threads of gravity. Careful science resists dramatic conclusions. Instead of declaring that we live inside a cosmic hole, astronomers describe probabilities, gradients, and tendencies. They acknowledge what is well supported and what remains open to refinement. This approach does not weaken understanding, it strengthens it. There is also a quiet humility in this stance. The universe does not owe observers clear labels. It offers patterns that must be interpreted cautiously. Boundaries emerge gradually, not sharply. Positions depend on scale, not slogans. In this light, the most accurate answer to the question is not a simple yes or no. It is that our galaxy occupies a region influenced by a nearby void, likely close to its edge rather than deep within it. That conclusion fits the available evidence while leaving room for future refinement. As new surveys map the universe more completely, this picture will sharpen. Boundaries will be traced with greater confidence. Motions will be measured more precisely, but the underlying complexity will remain. Location will still depend on perspective. Perhaps the most reassuring aspect of this uncertainty is its calmness. Nothing urgent hinges on the answer. Whether near or inside, the Milky Way continues its slow orbit. Galaxies drift. Space expands. Time unfolds without regard for labels. In the end, the question of position reveals something deeper than location. It shows how understanding emerges through careful measurement, cautious interpretation, and a willingness to live with partial answers. The universe is vast, layered, and patient. Our descriptions of it must be the same. So are we actually inside the whole? The careful response is that we are close enough to feel its presence, yet connected enough to remain part of a larger structure. A position defined not by certainty, but by context. And in a universe shaped by gradients rather than edges, that may be the most accurate answer available. One of the more intriguing questions to emerge from studying our cosmic neighbourhood concerns how fast the universe appears to be expanding around us. On the larger scales, expansion is remarkably uniform. Galaxies recede from one another in a smooth, predictable way, and the relationship between distance and speed holds across enormous spans of space. Yet when astronomers look closer to home, the picture becomes slightly more complicated. Measurements of the expansion rate in our local region sometimes suggest that space here may be stretching a little faster than average. The difference is not dramatic. It does not announce itself loudly. It appears as a small tension between measurements made nearby and those made across much larger distances, subtle enough to be debated, persistent enough to invite careful attention. To understand why this matters, it helps to think about how expansion is measured in the first place. Astronomers estimate how fast the universe is expanding by comparing how far away galaxies are with how quickly they appear to be moving away. Light plays a central role in this process. Its stretching reveals motion. Its brightness and other properties help estimate distance. Combine enough measurements, and a rate of expansion emerges. Ideally, that rate should be the same everywhere, once averaged over large enough scales, and on the larger scales it mostly is, but nearby measurements are affected by local conditions. Galaxies do not only move because space is expanding, they also move because gravity pulls them toward dense regions and allows them to drift away from emptier ones. This is where local density enters the story. If a region of space contains less matter than average, gravity there is slightly weaker. Galaxies in such a region experience less pull from their surroundings. As a result, they can drift apart a little faster than galaxies embedded in denser environments. From within that region, expansion may appear slightly enhanced. This idea has led some astronomers to ask whether our proximity to a large underdense region could influence local measurements of the expansion rate. If the Milky Way sits near or within a void, could that affect how fast nearby galaxies appear to be receding? Could local emptiness be subtly shaping our view of cosmic expansion? Several researchers have explored this possibility using both observations and models. The suggestion is not that the universe behaves differently here in any fundamental way, but that measurements taken in a locally underdense region might not perfectly represent the global average. The expansion itself would still be uniform on large scales. The difference would lie in how it is perceived locally. This proposal has an appealing simplicity. It connects large-scale structure with local observation. It offers a potential explanation rooted in known physics rather than exotic new ingredients. But simplicity alone is not enough. The idea must be tested carefully against data. When astronomers examine this explanation closely, the picture becomes nuanced. Local density does have an effect on galaxy motion. That much is well established. Voids influence how matter flows. Galaxies near them drift in characteristic ways. However, whether this influence is strong enough to account for the observed differences in expansion, measurements, remains uncertain. Some studies suggest that the effect could contribute modestly. Others find that it falls short. The outcome depends on how large and how empty the local region is assumed to be, and on how measurements are selected and interpreted. Small changes in assumptions can shift conclusions noticeably. This is why the discussion remains active rather than resolved. There is no single decisive test that settles the matter. Instead, evidence accumulates slowly, weighed and reweighed as methods improve. It is also important to note that not all astronomers agree on how significant the discrepancy is to begin with. Measurements of cosmic expansion rely on complex chains of inference. Distance estimates carry uncertainties. Calibration matters. Independent methods do not always align perfectly. Distinguishing between systematic effects and genuine physical differences is an ongoing challenge. Because of this, void-based explanations are treated with caution. They're explored as possibilities, not adopted as conclusions. Researchers test them against simulations, compare them to alternative ideas, and look for signatures that would clearly support or rule them out. There is a healthy restraint in this approach. The history of astronomy is filled with examples where apparent anomalies faded as data improved. It is also filled with cases where small discrepancies led to major breakthroughs. The difference lies in patience and care. The idea that local structure could influence local measurements is not controversial in itself. What remains debated is the scale of that influence. Is it a small correction or a significant factor? Does it explain part of the difference or only a tiny fraction? These are questions of degree, not direction. From a broader perspective, this debate highlights something reassuring about modern cosmology. Disagreements are not about whether expansion exists or whether gravity works. They're about refining measurements to higher precision. The framework remains solid even as details are examined closely. There is also an important conceptual point here. Expansion is not something that happens independently of structure. Space expands everywhere, but matter responds to gravity locally. These two processes overlap. Untangling their effects requires careful modelling and clear thinking. Gentle humour sometimes helps to keep this grounded. Measuring the universe from inside it is a bit like trying to estimate the speed of a river while floating along in the current. Local eddies and calm stretches can make the flow feel faster or slower, even though the river as a whole moves steadily onward. In the same way, living near a void might make expansion feel slightly different without changing its global behaviour. Whether this effect is large enough to matter remains an open question. What is clear is that astronomers do not rush to conclusions. Claims are tested from multiple angles. Independent teams check one another's work. Alternative explanations are considered seriously. This slow, methodical process is a strength, not a weakness. As new surveys extend farther and measure distances more precisely, the picture continues to sharpen. Larger volumes reduce the influence of local quirks. Better calibration reduces uncertainty. Over time, the role of local structure in expansion measurements will become clearer. For now, the expansion rate question remains a topic of careful discussion rather than firm resolution. Local measurements hint at complexity. Global measurements provide stability. Reconciling the two is an active area of research, approached with curiosity rather than urgency. What matters most for this story is not which explanation ultimately proves correct, but how the question is handled. The presence of debate reflects a field alive with inquiry, guided by evidence and tempered by caution. Whether local emptiness plays a role or not, the universe continues to expand calmly. Galaxies drift apart, structures evolve, voids deepen gently. The broader picture remains unchanged even as details are refined. In that sense, the expansion rate question is less about cosmic drama and more about cosmic precision. It reminds observers that understanding improves not through bold declarations, but through careful measurement, patient comparison, and a willingness to sit with uncertainty while the data slowly speaks. When the idea of a cosmic whole enters the conversation, it is natural to wonder whether it changes anything meaningful about life, physics, or the long-term stability of the universe. The phrase itself can sound dramatic, as though something fundamental might be missing or broken. In reality, living near or even within a cosmic void carries far fewer consequences than the name suggests. The most important point is also the simplest. The laws of physics do not change inside a void. Gravity still works the same way. Light still travels at the same speed. Atoms behave as they always have. The same physical principles that govern dense clusters of galaxies also govern the quietest regions of space. A void is not a different kind of universe. It is the same universe, just less crowded. If the Milky Way were located deep inside a void rather than near its edge, daily experience would remain entirely unchanged. Stars would still orbit the galaxy's centre. Planets would still circle their stars. Chemistry would proceed as usual. There would be no sudden dimming of the sky, no weakening of forces, and no cosmic instability creeping in from the edges of space. On human timescales, nothing about a void is urgent. The motions involved are slow beyond imagination. Galaxies drift over millions of years. Structures evolve over billions. From the perspective of a human lifetime, the universe is essentially frozen in place, regardless of local density. Even on astronomical timescales, the differences are subtle. Galaxies in voids tend to experience fewer interactions. They collide less often and evolve more gently. But this does not make them fragile or unstable. If anything, it can make them quieter places, shaped more by internal processes than by frequent external disruption. For the Milky Way, this means that proximity to a void does not threaten its structure or future. Our galaxy is not being pulled apart or pushed into emptiness. It follows its orbit, interacts occasionally with neighbours, and evolves at its own measured pace. The surrounding environment influences motion slightly, but never violently. One area where location does matter is interpretation. Astronomers must account for local structure when analysing data. Measurements of galaxy motion, distance, and expansion can be influenced by nearby density variations. This does not invalidate the measurements. It simply means they must be understood in context. In this sense, a cosmic whole changes how observations are read, not how reality behaves. It affects perspective, not physical law. Scientists adjust for these effects as part of careful analysis, much as a photographer adjusts for lighting when interpreting an image. There is also no sense in which voids are dangerous. They do not expand aggressively. They do not swallow matter. They are not growing at the expense of everything else. They grow quieter as matter elsewhere gathers, but this is a passive process, unfolding slowly and evenly. The word whole can be misleading here. It suggests absence where something should be. A cosmic void is not a gap torn into the universe. It is a natural outcome of how matter distributed itself over time. Nothing is missing. Nothing has been removed. This distinction is important for emotional reasons as well as scientific ones. Humans are sensitive to ideas of emptiness and isolation. A quiet region can feel unsettling if framed incorrectly. In reality, voids are simply part of the cosmic landscape, as ordinary as mountains and valleys on Earth, just vastly larger. Even light-hearted comparisons can help. If the universe were a loaf of bread, voids would be the air pockets that formed as it rose. They do not weaken the loaf. They give it structure. Without them, the texture would be entirely different. Another question that sometimes arises is whether living in a void affects cosmic destiny. Does it change the fate of the universe as a whole? The answer is no. The long-term evolution of the universe depends on its overall composition and expansion, not on local variations in density. Voids and clusters are details in a much larger story. On the larger scales, expansion continues smoothly. Galaxies recede, space stretches. Local environments shape motion slightly, but they do not alter the global trajectory. Whether a galaxy sits in a dense cluster or near a void, the universe expands all the same. This is why astronomers are careful to separate dramatic language from actual consequences. Terms like cosmic whole are descriptive shortcuts, not warnings. They capture attention, but they do not imply risk. The real significance of voids lies in what they teach about structure and history. They reveal how small differences in the early universe grew over time. They help test models of gravity and matter. They provide quiet laboratories for studying galaxy evolution under gentle conditions. In practical terms, voids offer astronomers opportunities rather than threats. Their simplicity makes certain measurements cleaner. With fewer nearby objects to interfere, some signals become easier to interpret. In this way, emptiness can be useful. There is also a philosophical calmness to this realization. Living near a void does not place us on the edge of anything meaningful. It does not signal fragility or isolation. It simply reflects where matter happened to gather, guided by gravity and time. If anything, voids remind observers that the universe is comfortable with imbalance. It does not insist on uniformity. It allows dense regions and sparse ones to coexist, each shaping the other without conflict. So does a cosmic whole change anything? In practical terms, very little. The sky remains the same. Physics remains steady. The future unfolds as it would have anyway. What does change is understanding. Recognizing the presence of a void refines how astronomers interpret motion and structure. It adds nuance, not alarm. It deepens context, not concern. In the end, a cosmic void is not a threat or a flaw. It is a quiet feature of a universe that builds complexity from simple rules. Its presence alters interpretation, not reality. And in a cosmos defined by vast scales and patient processes, that distinction makes all the difference. Whenever astronomers draw a map of the universe, they do so with an important caveat in mind. Every map is incomplete, not because of carelessness, but because the universe is vast, faint, and reluctant to give up its details easily. This raises a natural and necessary question. Could what appears to be emptiness sometimes be a limitation of observation rather than a feature of reality? Surveying the universe is not like surveying land on Earth. There is no fixed vantage point, no overhead view. Observers sit inside the system they're trying to measure, surrounded by dust, gas, and light from nearby objects. Every observation is filtered through distance, brightness, and the sensitivity of instruments. One of the most important limitations comes from brightness. Galaxies vary enormously in how much light they emit. Large spirals and active galaxies can be seen across vast distances. Small, faint galaxies are far more difficult to detect. As distance increases, even moderately sized systems fade below detection limits. This creates a natural bias in any survey. In practice, this means that maps of the universe are weighted toward the brightest objects. Regions that appear empty may still contain faint galaxies that current instruments cannot easily see. The farther away a region lies, the more severe this effect becomes. What looks like a void may be quieter than average, but not as empty as it first appears. Astronomers are well aware of this and take steps to correct for it. Statistical methods estimate how many faint objects are likely missing from a given region. Surveys are carefully calibrated to account for sensitivity limits. Still, these corrections rely on assumptions, and assumptions always introduce uncertainty. There is also the issue of coverage. No single survey observes the entire sky at the same depth. Some regions are mapped in exquisite detail. Others are sampled more sparsely. Observational priorities, telescope time, and technical constraints shape where data is richest and where it is thinner. This uneven coverage can introduce patterns that resemble structure. A gap in data can masquerade as a gap in matter. Distinguishing between the two requires careful cross-checking between independent surveys using different instruments and techniques. Dust within our own galaxy adds another layer of complexity. The Milky Way contains clouds of gas and dust that block light from beyond. In certain directions, distant galaxies are partially hidden or entirely obscured. This creates what astronomers sometimes call zones of avoidance, where the map becomes patchy, not because the universe is empty, but because our view is blocked. Correcting for this requires observations at different wavelengths, some of which pass through dust more easily than visible light. Each wavelength reveals a slightly different picture. Combining them improves clarity, but also adds complexity. Distance measurement itself introduces uncertainty. Estimating how far away a galaxy lies is not always straightforward. Different methods apply at different distances, each with its own assumptions and sources of error. Small uncertainties accumulate when building large-scale maps. These uncertainties do not invalidate the maps, they define their resolution. Just as a low-resolution image can show the outline of a landscape without revealing fine detail, cosmic surveys capture broad structure, even when individual features remain fuzzy. This is why astronomers speak in terms of statistical structure, rather than absolute certainty. A void is identified not because absolutely nothing is present, but because far less is present than average. The confidence lies in comparison, not in total absence. Future telescopes promise to sharpen this picture considerably. Instruments with greater sensitivity will detect fainter galaxies across larger volumes of space. Deeper surveys will fill in regions that currently appear sparse. Improved distance measurements will refine the placement of structures. As these tools come online, some voids may shrink slightly. Others may reveal faint populations previously unseen. But the overall pattern is expected to remain. Even with improved data, the universe does not become smooth. Contrast persists. This expectation is based on experience. Each new generation of surveys has filled in detail without erasing large-scale structure. Filaments remain, clusters stand out, voids endure, even as their interiors become better populated in the data. There is a quiet lesson here about scientific humility. Astronomers do not assume that current maps are final. They are working models, always subject to revision. Claims are phrased carefully. Conclusions are stated with margins of error and degrees of confidence. This humility is not a lack of confidence in science. It is a recognition of complexity. The universe does not reveal itself all at once. Understanding deepens gradually as tools improve and perspectives widen. It is also worth noting that uncertainty is unevenly distributed. Some aspects of cosmic structure are known with high confidence. Others remain fuzzy. Large-scale patterns are robust. Small-scale details are still being refined. Knowing which is part of the discipline. Gentle humor helps keep this grounded. Mapping the universe with limited instruments is a bit like trying to understand a forest at night using a flashlight. The largest trees are obvious. The spaces between them are harder to judge. As the light improves, more detail appears, but the forest does not suddenly turn into a meadow. In this way, emptiness in astronomy is always provisional. It is a statement about what is seen relative to what is expected, given current tools. As expectations and tools evolve, interpretations adjust. What matters is that this process is built into the method. Astronomers expect their maps to improve. They design surveys to overlap and cross-validate. Disagreements are investigated rather than ignored. This continual refinement is a feature, not a flaw. The question of misinterpretation is therefore not an accusation but a discipline. Asking whether the map could be misleading is part of responsible science. It keeps conclusions flexible and grounded, so could we be misinterpreting the map? In detail, almost certainly. In broad outline, very unlikely. The universe is not smooth. Matter gathers unevenly. Large underdense regions exist. The precise boundaries and contents of those regions will continue to be refined. This balance between confidence and caution defines modern cosmology. Patterns are trusted when they persist across methods, instruments, and models. Details are treated gently, allowed to settle as data improves. In the end, cosmic maps are conversations between observation and interpretation. Each new survey adds a voice. Over time, a consensus forms, not through certainty alone, but through consistency. The presence of voids in the universe is one of those consistent results. Even as maps sharpen and details fill in, the quiet spaces remain. They may be less empty than first imagined, but they are still quieter than average. Recognizing the limits of observation does not weaken this conclusion, it strengthens it. It shows that the understanding is robust enough to survive scrutiny, revision, and refinement. And perhaps that is the most reassuring outcome. The universe can be mapped imperfectly, interpreted cautiously, and still reveal a coherent structure. Not because observers insist on it, but because gravity, time, and matter have arranged things that way. Scientific humility does not erase the picture, it clarifies it. Once the idea of a cosmic whole enters the mind, it can feel strangely personal. The question becomes not just where the Milky Way sits, but whether that position is unusual. whether it places us somewhere rare or exceptional. The wider view of the universe offers a calming answer. Cosmic voids are not isolated curiosities. They are everywhere. As astronomers extended their surveys farther and farther from our local region, they found the same pattern repeating again and again. Dense clusters of galaxies linked by filaments, vast, quiet regions opening between them. These underdense spaces appear at every scale large enough to reveal structure. Wherever matter gathers unevenly, voids follow naturally. Some of these voids are enormous. They span distances so large that light takes hundreds of millions of years to cross them. Others are smaller, tucked between nearby filaments like gentle hollows in a rolling landscape. Together they fill a substantial fraction of the universe's volume. In fact, most of space lies inside voids rather than inside dense clusters. This can feel counterintuitive. When looking at astronomical images, attention is naturally drawn to bright galaxies and glowing nebulae. Darkness fades into the background. But in terms of sheer volume, emptiness dominates. The universe is mostly quiet space, shaped by gravity but lightly populated. Large voids have been identified in many directions. Some lie relatively nearby on cosmic scales. Others stretch far into the observable universe. Each one differs slightly in size and shape, influenced by the surrounding distribution of matter. None stand alone. They form a network of low-density regions that weave through the cosmic web just as filaments do. What is striking is not their existence, but their consistency. Voids appear wherever large enough volumes are examined. They are not rare accidents or special cases. They are expected features, arising naturally from the same processes that create galaxies and clusters. This broader context helps soften the idea that our location is somehow special. The Milky Way's proximity to a void does not place it in a privileged or isolated position. Many galaxies find themselves in similar environments. Some sit near the edges of voids, others drift within them. Some lie between multiple empty regions balanced by filaments on all sides. From the perspective of the universe as a whole, there is nothing unusual about this. Matter does not fill space evenly, so most locations will lie closer to emptiness than to density. Being near a void is not an exception, it is the norm. Calm repetition of scale helps here. Think in tens of millions of light years, then hundreds of millions, then billions. At each step the same pattern repeats. Structure and emptiness interlock. Dense regions never dominate the entire volume. Voids never swallow everything. Balance persists across scales. There is also a gentle reassurance in the fact that no void appears truly isolated. Each one is shaped by its neighbours. Filaments press against its boundaries. Clusters anchor its edges. Even the largest empty regions are part of a larger structure, connected indirectly to everything else. This interconnectedness means that location is always relative. A galaxy might be deep within a void when viewed from one scale, yet close to a filament when viewed from another. The universe does not provide a single, definitive label for place. It offers gradients and relationships instead. Astronomers often describe voids as bubbles packed together, each one pushing gently against the next. The analogy is not perfect, but it captures something essential. No bubble exists alone. Each is shaped by contact. Each helps define the shape of its neighbours. Seen this way, the Milky Way's environment becomes less mysterious. It is one example among many, shaped by the same rules that apply everywhere. There is no cosmic centre reserved for special observers, no unique vantage point where the universe behaves differently. This idea aligns with a long-standing principle in astronomy. Observers are not privileged. The universe does not arrange itself around any single location. What we see locally reflects global processes playing out everywhere. Gentle humor can help ground this perspective. If the universe were a beach, galaxies would be grains of sand clumped by the wind. Voids would be the spaces between those clumps. Standing in one gap might feel noticeable, but it would not be remarkable. Similar gaps stretch across the entire shore. The calming repetition of scale reinforces this point. Voids appear nearby, voids appear far away, voids appear at every distance large enough to measure structure. Each one differs slightly, but all share the same origin. This repetition also strengthens confidence in understanding. When a feature appears once, it invites curiosity. When it appears everywhere, it becomes explanation. The widespread presence of voids tells astronomers that they are not artifacts of observation or quirks of local history. They are built into the universe's design. Importantly, this does not diminish the uniqueness of individual galaxies or regions. Every location has its own story, shaped by local conditions and history. But uniqueness exists within a shared framework, not outside it. The Milky Way's story is one of many. Its proximity to a void influences motion slightly. Its position within a filament shapes its interactions. None of this separates it from the cosmic average. It places it firmly within it. This perspective helps dissolve any lingering sense of isolation. Being near emptiness does not mean being cut off. Gravity connects regions across vast distances. Light carries information across billions of years. Even the quietest void is threaded with influence. From a broader view, the universe resembles a vast tapestry woven from matter and space together. Voids are not gaps in the weave. They are part of the pattern, giving contrast and shape to the whole. Understanding this helps reframe the original question: are we living in a cosmic whole? In one sense, many observers are. In another, no one truly is. The universe does not divide cleanly into wholes and non-wholes. It offers a continuous landscape of density and emptiness. The calming truth is that our location does not stand out. It echoes countless others. The same processes that shaped our surroundings shape the surroundings of galaxies billions of light years away. There is comfort in this repetition. The universe is not improvising wildly from place to place. It follows patterns. It repeats itself. It builds structure through familiar rules applied patiently across time and space. So when thinking about cosmic wholes, it helps to zoom out until the question loses its sharpness. The Milky Way sits where matter happened to gather, next to where matter did not. This is not unusual. It is expected. In that expectation lies reassurance. The universe is vast, but it is also consistent. Wherever one looks, structure and emptiness coexist. Voids open, filaments stretch, clusters shine, and across it all, the same quiet physics continues its work. Our place within this pattern is not special, but it is perfectly ordinary in the most cosmic sense of the word. Emptiness has a way of unsettling the human mind. A quiet room can feel awkward. An empty street can seem eerie. A pause in conversation often invites discomfort. From early on, absence is learned as something to fill, correct, or avoid. When that instinct meets the idea of vast cosmic emptiness, the reaction can be surprisingly emotional. Part of this comes from how humans experience space. In daily life, empty places often signal loss or abandonment. A vacant house suggests someone has left. An empty plate means hunger has already happened. Absence implies that something expected is missing. This association runs deep, shaping how emptiness is interpreted long before the universe enters the picture. When the same word is applied to space itself, those emotional habits come along for the journey. A cosmic void sounds like a failure of formation, a hole where something should be. The imagination fills the silence with unease. But this response reflects human psychology more than cosmic reality. In the universe, emptiness does not carry the same meaning. A void is not a wound or a gap. It is a region shaped by the same physical laws as everything else, just with fewer galaxies passing through. Nothing has gone wrong there. Nothing has been removed. The universe simply did not place much matter in that location. This difference in meaning is subtle but important. Human emptiness often arises from change. Something once present is now gone. Cosmic emptiness often arises from continuity. Matter flowed elsewhere, guided by gravity, leaving behind regions that were always relatively sparse. There's also a difference in scale that the mind struggles to accommodate. On Earth, emptiness is usually small and temporary. A quiet space rarely stays quiet for long. In the universe, emptiness can span hundreds of millions of light years and persist for billions of years. It is stable, not transitional. Understanding this helps shift perspective. A cosmic void is not waiting to be filled. It is not unfinished. It is part of a balanced structure that includes dense regions as well. Peaks and valleys exist together. Remove one, and the other loses definition. This contrast reveals something about how meaning is assigned. Humans tend to value presence over absence, activity over quiet. Brightness attracts attention. Darkness recedes. In astronomy, the same bias exists. Telescopes and images highlight luminous objects, while the spaces between them fade into the background. Yet those spaces are doing important work. They shape motion. They influence growth. They define structure by contrast. Without emptiness, there would be no pattern, only uniformity. The discomfort with emptiness may also come from uncertainty. Empty spaces hide fewer clues. There are fewer objects to observe, fewer signals to interpret. For a species that relies on patterns and feedback, this can feel like standing at the edge of understanding. The mind prefers places where information is abundant. Cosmic voids challenge that preference. They invite patience. They offer less immediate reward. They require inference rather than observation. In doing so, they remind observers that not all knowledge comes from accumulation. Some comes from noticing what is not there. This idea has a long history in science and philosophy. Absence can be as informative as presence. A missing sound in a pattern can signal structure. A gap in data can reveal a boundary. In cosmology, the distribution of emptiness tells a story just as clearly as the distribution of light. Keeping this grounded helps prevent drift into abstraction. Void does not mean nothingness. Space within a void still contains energy, particles, and the quiet background glow left from the early universe. Physical laws apply there without exception. The difference is not qualitative but quantitative. Gentle humour can help here. Calling a void empty is a bit like calling a library quiet. It is quieter than average, not silent. There is still activity, just at a slower, more restrained pace. There's also a lesson in scale and patience. The universe does not rush to fill every gap. It allows imbalance. It tolerates quiet. Over time, this produces complexity rather than chaos. Humans often seek symmetry and completeness. The universe is content with variation. Reflecting on this can soften the instinctive unease. Emptiness becomes less a sign of absence and more a sign of balance. Dense regions exist because empty ones do. Movement happens because there is room to move. Growth occurs because there is space to grow into. This perspective can extend beyond astronomy. It touches on how space and silence function in other areas of life. A pause in music creates rhythm. White space in writing improves clarity. Silence allows rest. Emptiness, in these contexts, is not a failure, but a feature. The universe seems to agree. Its larger structures are shaped as much by what is not there as by what is. Voids give form to filaments. Quiet regions define busy ones. Together they create a coherent whole. There is also humility in accepting this. The universe is not arranged for human comfort. It does not prioritize brightness or density. It follows simple rules and allows outcomes to emerge. Emptiness is one such outcome. Importantly, this emptiness does not imply isolation. Even the quietest void is part of the larger cosmic network. Gravity connects regions across vast distances. Light from distant galaxies passes through voids on its journey. Nothing is cut off. Understanding emptiness in this way dissolves the idea of cosmic loneliness. A galaxy near a void is not abandoned. It is simply situated where matter is sparse. The universe remains connected, structured, and active. When emptiness is reframed as structure rather than absence, its emotional weight changes. It becomes something to understand rather than something to fear. The mind can rest in the idea that not all spaces need to be filled to have meaning. In this light, the philosophy of emptiness becomes surprisingly practical. It teaches patience. It encourages perspective. It reminds observers that meaning does not always arrive in the form of abundance. The universe offers vast spaces where little happens, and it does so without apology. Those spaces are not mistakes. They are part of a larger balance that allows complexity to arise elsewhere. Recognizing this can bring a quiet sense of calm. Emptiness no longer signals loss, it signals structure. Silence no longer implies absence, it implies space. And in a universe shaped by gravity, time, and scale, space itself is not a void to be feared, but a canvas on which everything else unfolds. There is a natural human tendency to wonder whether a particular position in the universe carries special meaning. When a new feature is discovered nearby, especially one with a name as evocative as a cosmic void, it can feel tempting to treat that location as exceptional, as though standing near emptiness must say something profound about where observers happen to be. Astronomy has learned gently and repeatedly to resist that instinct. On the largest scales, the universe does not arrange itself around preferred viewpoints. It does not place observers at centers or edges for narrative effect. Instead, it follows simple rules applied everywhere, producing patterns that repeat across vast distances. From that perspective, the Milky Way's surroundings are not unique. They are familiar. Wherever one imagines an observer placed within the cosmic web, a similar view would emerge. Dense regions would cluster in some directions. Quieter expanses would open in others. Filaments would stretch across the sky. Voids would occupy much of the volume. The specific arrangement would differ, but the overall pattern would feel recognizable. This is an important shift in perspective. Rather than asking whether our location is special, astronomers ask whether it is typical. Typicality does not mean uniformity. It means consistency within variation. Each location has its own details, but the underlying structure remains the same. In a universe shaped by gravity and expansion, most galaxies will not sit at the densest nodes. Those regions are rare by definition. Most will not sit in the deepest emptiness either. Most will occupy intermediate positions near filaments, adjacent to voids, influenced by both. From this viewpoint, the Milky Way fits comfortably within expectations. It resides in a modest group, near a filament, close to a large underdense region. None of these features are rare. Together, they describe a very common cosmic environment. The feeling of specialness often arises because observations are made from a single point. Everything appears to radiate outward from that location. Structures seem arranged around the observer simply because the observer is at the center of their own map. Change the viewpoint and the pattern reorients itself naturally. Astronomers account for this effect carefully. They do not assume that patterns seen from one location reflect a unique position. Instead, they compare observations across many regions, testing whether similar structures appear elsewhere. They do. Voids appear everywhere. Filaments stretch in every direction. Clusters gather wherever conditions allow. The universe repeats itself not exactly, but reliably. This repetition is what allows confidence in large-scale understanding. There's also a comforting implication here. If our surroundings are typical, then they are stable. Exceptional positions often suggest fragility or imbalance. Typical ones suggest equilibrium within a broader pattern. The Milky Way is not perched precariously on the edge of anything meaningful. It is embedded in a structure that has persisted for billions of years. This does not diminish the wonder of observation. Typicality does not mean dullness. A coastline is typical, but still beautiful. A forest is typical, but endlessly varied. The universe manages to be both ordinary in structure and extraordinary in detail. Gently pushing back against cosmic exceptionalism also helps clarify what questions are worth asking. Instead of asking why the universe placed us here, it becomes more productive to ask how structures form everywhere. Instead of focusing on position as destiny, focus shifts to process and pattern. This perspective has guided astronomy for centuries. Earth was once thought to occupy a central position. That idea gradually gave way to a broader understanding. The Sun was not special. The galaxy was not special. Even our local cluster is not special. Each step outward reduced the sense of privilege while increasing understanding. The presence of a nearby void follows the same pattern. It feels noteworthy because it is close. It feels significant because it has a name. But in context, it is one of many. Its properties fall within expected ranges. Its influence behaves as predicted. If observers were located in another galaxy far across the universe, they would likely describe their surroundings in similar terms. A local group. Nearby filaments. Large empty regions shaping motion. The language might change. The coordinates would differ. The structure would remain familiar. There's a quiet reassurance in this symmetry. The universe does not single out observers for special treatment. It applies the same rules everywhere. Gravity pulls, expansion stretches, matter gathers unevenly, voids form naturally. Life, where it arises, does so within these ordinary conditions. Gentle humour can help soften the idea. Discovering that one's cosmic address is typical is a bit like learning that one lives in a perfectly average neighbourhood. It may not sound glamorous, but it comes with stability, predictability, and plenty to observe. Typicality also guards against overinterpretation. When a feature is seen as exceptional, it invites dramatic explanations. When it is seen as common, it invites careful analysis. The latter tends to lead to better science. Maintaining this balance is part of responsible interpretation. Astronomers avoid attaching significance beyond what evidence supports. They describe what is observed, compare it to models, and assess whether it fits expected patterns. In this case, it does. There is also an emotional aspect to this reassurance. Humans often search for meaning in position. Where something sits can feel important. The universe gently counters that instinct. Meaning does not come from placement. It comes from understanding. Being typical does not make observation less valuable. In fact, it makes it more reliable. Observations made from a typical location are more likely to reflect general properties rather than special cases. This strengthens conclusions rather than weakening them. From this standpoint, the Milky Way's environment becomes a useful reference rather than a curiosity. It represents a common setting in which galaxies evolve. Studying it helps illuminate processes that operate elsewhere as well. The universe, in its vastness, seems to favour repetition over uniqueness. Patterns recur, structures echo one another, Complexity arises not from special cases, but from simple rules applied everywhere. This repetition does not erase individuality. Each galaxy still has its own history. Each void has its own shape. Each region reflects local conditions, but none of these details elevate one location above all others. The reassurance lies in this ordinariness. The Milky Way is not balanced on the edge of a cosmic anomaly. It is not hidden away in an unusual corner. It is situated where countless other galaxies are situated, shaped by the same slow forces. Understanding this helps settle the mind. The universe is not fragile. It is not delicately arranged around observers. It is robust, patterned, and patient. In the end, the discovery of nearby emptiness does not confer special status. It places the Milky Way firmly within the cosmic average, a galaxy among many, near fullness and emptiness both, influenced by structure rather than isolated from it. And in a universe that values consistency over exception, that ordinary position is not disappointing. It is quietly reassuring. Even after decades of observation, simulation, and careful measurement, there remain important things scientists do not yet know about cosmic voids and our place among them. This uncertainty is not a flaw in the process. It is the natural edge of understanding in a universe that is vast, subtle, and patient. One of the most fundamental open questions concerns the precise shape and extent of nearby voids. While large underdense regions are clearly present, their boundaries are not sharply defined. Density changes gradually, not abruptly. This makes it difficult to say exactly where a void begins and where it ends. Different methods produce slightly different outlines, all reasonable, none absolute. Closely related to this is the question of depth. How empty is a given void, really? Observations show that voids contain fewer galaxies than average, but the true population of faint and tiny systems remains uncertain. Some galaxies may simply be too dim to detect with current instruments. Others may exist in forms not yet fully catalogued. There is also the role of dark matter within voids. While it's clear that voids contain less dark matter than denser regions, the exact distribution is still being studied. How smoothly is it spread? Does it clump on small scales? How does it influence the slow evolution of galaxies that live in these quiet environments? These are questions that require both better data and refined models. Another area of active investigation involves galaxy motion. Astronomers can measure how galaxies move relative to cosmic expansion, but interpreting those motions is complex. Local gravitational influences overlap with global expansion. Separating these effects requires careful modelling and large samples. Small uncertainties in motion can lead to different interpretations of the surrounding mass distribution. There's also ongoing discussion about how representative our local region truly is. While evidence suggests it is typical, refining that conclusion depends on ever larger and more complete surveys. Sampling bias remains a concern. The more of the universe that is mapped, the more confident scientists can be that local observations reflect general behaviour rather than coincidence. Future surveys are designed with this goal in mind. They aim to observe wider areas of the sky, reach fainter objects, and measure distances with greater precision. By expanding both depth and breadth, these projects will reduce uncertainty and fill in gaps that currently limit interpretation. Improved sensitivity will allow astronomers to detect galaxies that are presently invisible, especially within voids. This will clarify whether void interiors are truly sparse or simply undercounted. Either outcome is informative. Both help refine understanding of structure formation. Better distance measurements will also sharpen maps of large-scale structure. Knowing where galaxies are in three-dimensional space, rather than just where they appear on the sky, is essential for understanding void geometry. Small improvements in distance accuracy can significantly improve clarity on large scales. Another open question involves the relationship between voids and cosmic expansion. While there is discussion about whether local density affects local expansion measurements, the magnitude of this effect remains debated. Future observations will help determine how much local environment influences what is measured and how much is due to other factors. None of these questions require dramatic new physics to be interesting. They are questions of refinement, not revolution. They reflect a mature field working carefully at the limits of precision. This slow pace is intentional. Astronomy has learned the value of restraint. Apparent surprises have often faded with better data. Genuine discoveries have emerged gradually, confirmed by independent methods and repeated observations. There is a temptation, especially in public conversation, to frame unknowns as mysteries waiting for sudden revelation. In reality, most progress happens quietly. New data slightly adjusts old conclusions. Models improve incrementally. Confidence grows through consistency rather than spectacle. This is particularly true for topics like cosmic voids, where the signals are subtle and the scales enormous. Nothing here lends itself to sudden change. The universe does not reveal itself through dramatic moments, but through accumulation. Trust in careful observation is built on this history. When astronomers say something is uncertain, it does not mean they are unsure of everything. It means they know exactly where confidence ends and where questions begin. That clarity is a strength. It is also worth remembering how much is already known. The existence of large-scale structure is well established. The role of gravity in shaping it is well understood. The presence of voids is not in doubt. What remains open are the details of boundaries, contents, and subtle influences. Gentle humor can help keep this perspective balanced. Science is less like solving a puzzle in one sitting, and more like adjusting a very large telescope, one careful turn at a time. Each adjustment improves the view slightly. None delivers the entire picture at once. Future instruments will continue this process. They will not overturn what is known, but refine it. They will sharpen outlines, reveal faint features, and reduce uncertainty. Each improvement will make the cosmic map clearer, but never complete. There will always be limits. The universe is finite in age, and light travels at a finite speed. Some regions will remain beyond observation. Some questions will remain partially unanswered. This is not failure, it is context. Scientists work within these limits deliberately. They do not speculate beyond what data can support. They test ideas, discard those that fail, and keep those that survive scrutiny. Over time, a reliable picture emerges. This method has earned trust. Predictions made decades ago about large-scale structure have been confirmed. Simulations anticipated patterns later observed. Models refined slowly have proven robust. There is no reason to expect that this careful approach will suddenly stop working. Uncertainty in this sense is not something to be resolved quickly. It is something to be managed thoughtfully. It guides where effort is directed and which measurements matter most. The quiet confidence of modern cosmology lies in this balance. It knows much. It admits what it does not know. It proceeds without urgency. For those listening, this can be reassuring. The universe is not poised on the brink of reinterpretation. Understanding deepens, but the foundation remains steady. Each unanswered question sits within a framework that has already proven reliable. Cosmic voids, our location near them, and their subtle effects are part of that ongoing refinement. They invite curiosity without demanding alarm. They encourage patience rather than speculation. In the end, what scientists still do not know is not a list of failures. It is a map of future understanding. Each open question marks a place where observation will eventually reach, where clarity will increase, where detail will sharpen. Until then, The universe continues as it always has. Galaxies drift. Voids expand gently. Structure evolves slowly. Observers watch, measure, and refine. Trust in careful observation has carried astronomy this far. It will continue to do so, one quiet improvement at a time. Living in a quiet part of the universe can sound unsettling at first. Quiet is often mistaken for absence. Stillness can feel like neglect. But when viewed through the lens of cosmic time and structure, quiet takes on a very different meaning. It becomes a sign of balance rather than loss, stability rather than isolation. A cosmic void is not an empty stage waiting for something to happen. It is a region where the universe has settled into a gentle arrangement. Matter gathered elsewhere. Gravity did its work patiently. What remains is not nothing, but calm. A place where large disturbances are rare and change unfolds slowly. This quietness carries with it a sense of longevity. Regions near voids tend to evolve at an unhurried pace. Galaxies experience fewer dramatic encounters. Their shapes are preserved longer. Their internal processes proceed without constant interruption. On the grander scales, this translates into stability, measured not in years or centuries, but in billions of years. Time behaves generously here. Nothing is rushing, nothing is collapsing. The universe is not poised on the edge of transformation. Instead, it stretches outward steadily, guided by the same laws that have shaped it since its earliest moments. Living near a quiet region means living within that steadiness. This perspective helps soften the idea of a cosmic whole. The word whole suggests something missing. The reality is closer to open space, room to breathe, a wide interval between structures that allows the universe to display contrast rather than crowding. In this setting, the Milky Way follows its path calmly. Stars orbit the galactic center as they have for billions of years. Planets trace their predictable routes. Nothing about the galaxy's internal rhythm is disrupted by the surrounding quiet. The night sky remains rich, layered, and luminous. Even the motion of the galaxy itself reflects this calm. Its drift through space is measured and gentle, influenced by distant structures rather than immediate pressure. The forces involved are vast but slow, acting over distances so large that urgency has no place. There is comfort in recognizing how little changes here, at least on timescales that matter to life. While galaxies elsewhere collide and clusters churn with activity, this region experiences fewer upheavals. The universe allows many environments to coexist, some busy, some quiet. Neither is preferred. Both are natural. This balance mirrors patterns closer to home. Rivers have rapids and stretches of still water. Weather alternates between storms and calm. Ecosystems include both bustling intersections and quiet refuges. The universe seems to follow the same principle on a far grander scale. Reframing emptiness as calm also changes how space itself is perceived. Space is not a void to be feared. It is a medium through which light travels, gravity acts, and time unfolds. Even where galaxies are sparse, space remains active, dynamic, and governed by consistent rules. Stability does not mean stagnation. The universe continues to evolve everywhere, including in its quiet regions. The pace is simply slower. Changes accumulate over immense spans of time, smoothing extremes and deepening structure without drama. This long view invites patience. It suggests that not everything needs to happen quickly to be meaningful. The most enduring features of the universe are shaped slowly, through countless small interactions rather than sudden events. There is also reassurance in knowing that quiet regions are not cut off. They remain connected to the broader cosmic web through gravity and the flow of space itself. Influence travels across voids. Light crosses them. Information moves through them. quiet does not mean disconnected. From this vantage point, the idea of living near a cosmic whole loses its weight. What remains is a sense of being situated within a vast balanced system that accommodates both activity and rest. Gentle humour can find a place here as well. If the universe were a city, some neighbourhoods would be busy intersections filled with constant traffic. Others would be quieter streets where things move more slowly. Both are part of the same city. Both are necessary. Living in a quieter area does not imply being overlooked. It implies being part of a system that values variety. The universe does not concentrate everything into a single place. It spreads out, allowing different regions to play different roles. This understanding encourages a softer relationship with cosmic scale. Instead of feeling small or isolated, there is an invitation to feel settled, to recognize that stability is not accidental. It is the product of consistent laws applied over vast spans of time. The universe has had billions of years to arrange itself. The patterns seen today are the result of that patience. Quiet regions persist because nothing compels them to change quickly. Dense regions persist because gravity holds them together. Together they form a whole that is neither chaotic nor static. As attention turns inward from the larger scales, this sense of calm can follow. The same universe that allows vast quiet spaces also allows moments of stillness closer to home. Space, in this sense, is not just something out there. It is a reminder that stillness has a place. This gentle settling does not require final answers. It does not demand certainty about boundaries or labels. It simply acknowledges what is already clear. The universe is structured. It is patient. It accommodates emptiness without discomfort. Living in a quiet part of the universe does not diminish meaning. It reframes it. Meaning arises not from being at the center of activity, but from being part of a larger, enduring pattern. As this exploration draws closer to rest, the emphasis shifts naturally from questions to perspective. The universe is vast, but it is also comprehensible in its broad strokes. It is complex but not hostile. It is quiet in many places, and that quiet is not a flaw. There is room here for reflection rather than conclusion. No need to force resolution. The universe does not hurry, and neither must understanding. Galaxies continue their slow journeys. Voids remain open and calm. Structures evolve at their measured pace. The Milky Way drifts gently through a region shaped by both presence and absence, activity and stillness. Seen this way, living in a quiet part of the universe is not something to overcome or explain away. It is something to notice, appreciate, and settle into. The cosmos does not ask to be filled. It allows space. And within that space, everything that exists continues to unfold, steadily and without urgency. In that steadiness there is reassurance. In that quiet there is structure. And in that structure there is a place where the universe simply is, vast and patient, offering room enough for stars, galaxies, and thought itself to drift gently onward. The question that began this journey was simple on the surface. Are we living in a cosmic whole? As the view widened and the scale stretched outward, that question softened rather than sharpened, not because it lacked meaning, but because meaning in the universe is rarely fixed to a single point. Location, it turns out, is always contextual. On one scale, the Milky Way is part of a small familiar group of galaxies. On another, that group drifts beside a vast region where matter is sparse. On still larger scales, both are threads within an immense cosmic web, repeating patterns found everywhere the universe is large enough to reveal itself. None of these perspectives cancel the others out. They coexist. Each one is accurate within its own frame. Asking whether we are inside a void or near one depends entirely on how far back the view is pulled and whether boundaries are drawn. The universe does not offer a single definitive address. It offers relationships. What becomes clearer with each layer is that emptiness is not the same as absence. The quiet regions of space are not holes torn into reality. They are part of its architecture. They shape motion, define structure, and allow contrast to exist. Without them, the universe would be smoother, simpler, and far less interesting. Emptiness in this sense is active without being busy. It participates without demanding attention. It gives shape by being less full, not by being nothing at all. Gravity still moves through it. Light still crosses it. Time still unfolds within it. There is something quietly reassuring in that idea. The universe is not packed edge to edge with urgency. It allows space. It tolerates imbalance. It unfolds at a pace that makes room for both growth and stillness. Seen from within this wider picture, the Milky Way's position feels less like isolation and more like belonging, not at the centre, not at the edge, simply situated, as countless other galaxies are, within a structure shaped by simple rules applied patiently across immense spans of time. The universe does not hurry to fill every gap, and it does not rush to provide final answers. Understanding deepens slowly, just as structure does. Patterns emerge through accumulation rather than revelation. That rhythm is easy to miss when attention is drawn only to brightness and activity. But it becomes clear when the quieter regions are allowed their place in the story. Calm is not a failure of formation. It is part of how the universe maintains balance. So the original question remains open, and that is exactly where it belongs. Not unresolved, but gently held. The universe is vast, structured, and patient. It does not rush, and neither must we. There is space enough here for curiosity without urgency, for understanding without finality, and for a quiet sense of belonging within something far larger than any single point of view.